Whoa, Nelly. Here we go, ladies and gentlemen. We're learning something brand new today. Titrations. Finally, something new, something that isn't the same thing over and over and over again. I actually really enjoyed this part of Chemistry 20. Titrations are pretty fascinating stuff. Um, Obviously, way more interesting if you were able to be here in person. But you know what? It is what it is. So we're going to get started here. Today's plan, we're actually going to learn something new today. Wonders never cease, right? So we're going to learn about a procedure called titrations. Basically, titrations are where we are mixing acids and bases, and we have an unknown concentration for one of them. So the main idea here is we use this procedure called titrations to figure out what the concentration is of either our unknown acid or our unknown base. So it's like basically a problem solving thing. The good news is it relies heavily on the stuff we've already done. So all that work we've been doing, the past week and a half, doing the same thing over and over and again, it's been building up to this. It's been basically getting us ready to do this. And this isn't really all that much more. It's just a new context for it. Let's go. So this is on page 21 of your handout, topic 4, titrations. The application of Stoic calculation principles applies also to solutions. That was what yesterday's lesson was all about. Most often, you will be required to use concentration and volume to find moles, because concentration is, of course, just moles per liter, and volume is usually in liters, right? So we're going to start with an example. This example right out the gates is a pretty tough one. It's not a titration example, but it's getting us used to this idea of mixing acids and bases, or at very least, well, yeah, I guess acids and bases, because ammonia is a base. So we got solutions of ammonia and phosphoric acid, and they're used to produce something called ammonium hydrogen phosphate, and it's a type of fertilizer. What kind of volume of 14.8 moles per liter of NH3 aqueous is needed for the ammonia to react completely with 1.0 kiloliters, that means 1,000 liters, of 12.9 moles per liter of your H3PO4, that's your phosphoric acid, to produce fertilizer. Anyway, let's get going on this one. First things first, the scariest thing about this is this ammonium hydrogen phosphate. If you look at your polyatomic ion chart, that's a thing right above your periodic table, you'll see that hydrogen phosphate is actually listed as being something called HPO4, and that it also has a 2 negative charge. Ammonium is hopefully a little bit familiar to us. Ammonium is NH4, and it has a positive 1 charge. It's like the only positive polyatomic ion that we really deal with in this course. So naturally, if we're going to combine these together, we need to have 2 ammoniums and just one of these HPO4s. And again, that's PO4. That wasn't very clear. Anyway, other things we know here, ammonia, of course, is NH3 that was given to us, and phosphoric acid is H3PO4. So let's just throw this together first things first in a balanced chemical equation. So we have NH3, that's your ammonia, reacting with H3PO4, that's your phosphoric acid, and that's producing ammonium hydrogen phosphate. Try saying that 6 times fast or whatever. Anyway, so this is going to be NH4. We'll need 2 of them, so it has an overall charge of positive 2 now, and then we'll just tack on an HPO4 on the end there. That's an absolute beast. That is like the most beefcakey thing we've actually made, like from scratch here, but that's just how it is. Next thing, we got to balance this. Oh my goodness. Okay, you might look at this and go, okay, we got to balance this. That's quite the task, because we've got like hydrogens that are broken up here and here, and there's only like 3 hydrogens here and 3 hydrogens here. Like the hydrogens seem to be the big problem here. They're all over the place. But just calm down. Don't worry about it. This is actually way easier to balance than you think. I was actually quite surprised too. PO4, just think of that as one piece, and there's another PO4 over here. That one's fine. H3 is there, but we got H here and H here, so we'll worry about the H's in a second. The other thing I want you to look at, though, is we have 1 nitrogen here, and technically we have 2 nitrogens over here, okay? So that would kind of hint to us that we're probably going to have to put a 2 in front of this. If we have to get rid of the 2 eventually, we can erase it, whatever, right? Let's just take stock of what we have now. We got 2 nitrogens here and 2 nitrogens here. Okay, so for now, those are balanced. We have 1 PO4 here, 1 PO4 here. Okay, great, now those are balanced. Now for our hydrogens, we have 2 times 3, so 6 hydrogens here, plus 3 hydrogens, so we got 9 hydrogens in total on the left side. And then notice we have 4 hydrogens here times 2, so we got 8 hydrogens, plus 1 more, so we got 9 hydrogens here too. That's it, right? That's it, it's balanced. Everything's now the same. We got 2 nitrogens on both sides, 9 hydrogens, and 1 PO4 on each side. We're good, that was already balanced. Whew, good, that was way easier than we thought. From there, remember, from the stuff we've been doing lately, find the number of moles of whatever you were given. Notice we were given the volume and the moles per liter, the concentration of H3PO4. We can use those two to find the number of moles of H3PO4. So in other words, we can just say this is 12.9 moles per liter equals some number of moles, we'll say it's N, over some number of liters, which we know is 1 kiloliter, so that's 1,000 liters. Multiply that over, you're going to find that N is going to be 12,900 moles. It's a lot of moles. And the other thing I want you to notice with that is technically what we would call 1 part, right? Because in our balanced equation here, there's only a 1 in front of this here, and there's a 2 in front of this. So this is only 1 part. So what that basically means for us is we're going to have to times this now by 2 to figure out the 2 parts, the amount of ammonia we have. If you just times that by 2, you are going to get 25,800 moles. That is representing 2 parts. Cool. Now, the reason that we need that is, remember, we're trying to find the amount of ammonia, in terms of a volume, that is, needed to react with this amount of H3PO4. So in order to do that, we would need this many moles. And if we're looking for volume, we can just use the concentration and the moles, right? So what I'm trying to spit out here, and just not doing a very good job at saying it, is we can just use the concentration of ammonia, 14.8 moles per liter. That was a concentration of ammonia, right? Set that equal to some number of moles. We have 25,800 moles, because remember that is 2 parts. There's a 2 here, so there's 2 parts of ammonia. And divide that by your unknown amount of liters, which we're just going to say is X. To solve for X, we just need to multiply it by X and then divide by 14.8 on both sides. And then just watch your sig digs. If you look back at the question, it looks like 3 sig digs is all we're really going to need here. So if you throw this in your calculator and then look for just 3 sig digs, well, first of all, I see my answer is 1,743 point a bunch of stuff. That's 4 sig digs though, so we actually unfortunately have no choice but to turn this into scientific notation. So just keeping 3 sig digs, so we'll just keep these 3 digits right here. We'll say it's 1.74, and you can say it's times 10 to the 3 liters. Or if you want to be really fancy, you can say it's X equals 1.74. This is 1,000 liters, 1,000 something liters. So we can just say it's kiloliters. Either one of those is just fine. Scientific notation probably keeps things a little bit more steady, but using kiloliters is fine. That's what those metric prefixes are there for, right? Metric is nice because it lets us do that, right? That's quite useful. Anyway, moving on. Example 2, this one is comparable to that last one we just did. A technician determines the amount concentration of sulfuric acid solution. In the experiment, a 10 milliliter sample of sulfuric acid reacts completely with 15.9 milliliters of this much moles per liter potassium hydroxide solution. Calculate the amount concentrations of the sulfuric acid. Because this is basically the same thing as the last question, I actually want you guys to pause the video here, see if you can get this one on your own, because it's great practice, and then we'll go over it in just a second. Okay, so I'm going to go over this one. Basically, the idea here is, as always, start with your balanced chemical equation. We know we have potassium hydroxide, that's KOH, and we also know we're dealing with sulfuric acid, which is H2SO4. So if you write your equation, it's going to be H2SO4 plus KOH is going to produce HOH, it's water, because of course an acid and a base will always, well, usually at least produce water in a neutralization reaction at least. So we have HOH plus the salt that's going to form, which is K and SO4. Well, K has a positive 1 charge, SO4 has a 2 negative charge, so it's going to be K2SO4. Next thing, of course, we got to balance this. I notice we have 2 hydrogens on both sides, so I'll put a 2 here. We also have 2 potassiums here, so I'm going to need to put a 2 here. And if you check everything out, you're actually going to see that that's now balanced. Next up, deal with the thing that you know stuff about, right? That's a real fancy way of saying it. But basically, we have potassium hydroxide here. We know our concentration, and we know how many liters we have, milliliters, but still liters. So we can actually use that to find our moles, right? Because if we can find moles, bingo, we've unlocked the rest of this. So from here, we can say we got 0.150 moles per liter equals some number of moles over 0.0159 liters, right? So I just turned this into liters, of course, by dividing it by 1,000. That's going to give me N equals, this is not going to be such a nice number, but 0.002385 moles. Now, what I want you to recognize, though, is this number of moles is 2 parts. Okay? Always think of your moles in terms of parts. It doesn't work with grams. It doesn't work with liters. It only works with moles. So that's 2 parts. We're looking, however, though, for the concentration of sulfuric acid. That's moles per liter of sulfuric acid. So we're going to need the number of moles of this. Notice this is just technically 1 part. So we need to divide this by 2 to get 0.00111925 moles, and that is 1 part. Woo, thrilling. All right, so last thing we got to do here. We now have our number of moles. We also have the number of liters of sulfuric acid that we're dealing with here. Concentration is moles per liter, so just moles divided by liters. We can just say that this is 0.00111925 moles divided by the amount of liters we have, which is 0.010. It's 10 milliliters, so 0.010 liters. Throw that in your calculator, and of course, because this is going to be your final answer, we should also worry about our sig digs. It looks like only 3 sig digs. That seems to be a common thing here. But to 3 sig digs, you're going to see that our concentration is 0.119 moles per liter. Awesome. Just amazing. Super thrilling, super thrilling. Okay, so you might be thinking, all right, Scott, at the beginning of the lesson, you said, oh, we're dealing with something new today. It's titrations. Oh, it's so fun. It's my favorite thing. Yay. Well, we haven't actually talked about what titrations are. We've just talked about mixing acids and bases, both this example and that last example. So here we go. Here's what a titration is. A titration is a process in which a measured amount of a solution is reacted with a known volume of another solution, which usually has an unknown concentration, until a desired equivalence point is reached. The equivalence point is the point in a titration where the ratio of the moles of each species involved exactly equals the ratio of the coefficients of the species in the balanced chemical reaction equation. Basically, what this is, when we're mixing an acid and a base, is your equivalence point is all of a sudden where you go whoosh, and you have a pH of 7, a perfectly balanced situation where you have now officially neutralized your solution. Of course, this definition that's on this page is a lot more, specific than that. But if you want to think of it as an equivalence point, it's just the whoosh point where all of a sudden your chemical reaction between your acid and base is neutralized. That's as good as we need, at least for chemistry 20. Chemistry 30 will go more advanced, I'm sure. Chemistry 20, that's all you need though. Now, how do we know we've hit equivalence point? That's the real question. You're mixing your acid and your base together. How on earth would you have known that an equivalence point is reached? You're probably thinking, do we really seriously have to get out a calculator and calculate this? The answer is no, you don't. When you're doing an experiment, the equivalence point is recognized by the fact that a special colored dye called an indicator will change color at the point that the acidic solution is exactly neutralized by the added, it says NaOH, but really it's just like the added base. You can use whatever you want. Basically what this means is in your Erlenmeyer flask, that's the name of this fancy little beaker kind of thing, right? It's not a beaker though, we should call it an Erlenmeyer flask. In this Erlenmeyer flask, you're going to have your acid. You could have a base in there if you want to do it the other way. It's just usually we put the acid in here. It really doesn't matter. It depends on your situation. We'll just say it's the acid for now. Not only are you going to have your acid in there, like let's say it's hydrochloric acid, you're also going to have an indicator. And again, an indicator is just a special chemical that is designed to change color at a specific point. If you have a look in your data booklet, I believe, I'm just going to look at mine right now just so I don't tell you some fake news here. Yep, it's on page 10. If you look in your data booklet, page 10, there's an entire list of a bunch of different chemicals that can be used as acid-base indicators. At the school, we have a whole bunch of these. Some of the common ones that I see just looking at this, I know methyl red, which is kind of halfway down. We use that one quite a lot. Another one that's very commonly used is bromothymol blue. It's just a couple under methyl red. Phenolphthalein is another one that's used down below. That's more used for more basic solutions. And as you can see, a pH range change is there. It's basically just those 3 that we use very commonly. But the other ones do come around, and I'm pretty sure we actually do have some of them lying around. Now, again, the whole idea here is you have your acid and your indicator in your Erlenmeyer flask. And as you drop some droplets of bases into there, eventually you're going to find that the solution is going to change color. And of course, the color change just depends on whatever indicator you used. You could use that chart on page 10 to help you out. But as soon as it changes color, that tells you you've hit the equivalence point. Now, right next to this Erlenmeyer flask in your notes, you'll see like there's this little grid thing. This is good for showing what we call an equivalence point graph, or a titration curve is another name for it. Basically, how it works is, think of this as a graph with an x-axis and a y-axis. The x-axis will always be the volume of your titrant, so whatever's like dripping down in here. In this case, we'll say it's the base, the volume of a base added. Along this side would be your pH. The bottom is always 0, the top is always 14, and the midpoint, of course, is 7. 7 is a totally neutral solution. So the volume of your base added, as that increases, of course, a base has a higher pH, so of course it's going to be raising your pH, but it doesn't follow a linear trend. You might think that as you add droplets to this acid, it's just going to go, oh, it's going to go up, 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 up. But in reality, the equivalence point happens, and it's a big surge all of a sudden. So here's what it would look like. As you start adding drops of base, your pH just kind of slightly goes up, just barely. And then all of a sudden, at a certain point, it'll go whoosh all the way up like this, and then it'll kind of flatline again. This whoosh happens in a very short time frame, right? So as you're dropping droplets in here, you're going to see that the color change of your solution is just going to switch really, really quick. Like it's just going to go boom from one color to the next instantly. Like one drop could make all the difference between like it wasn't changed and then one more drop and boom, it's totally changed color. This right here, right in the center of this huge swoosh, is your equivalence point. And that is the point, equivalence point. That's the point, of course, where you're going to see a color change. Yeah, so that's the basic idea, okay? Now, we should also talk about how to set up a titration. There's another video attached to our lesson with this. It was by Taunton River University. I'm going to get you guys to watch it after this lesson's over, but it shows how to set up a titration station and actually perform the experiment. Basically, here's what it looks like. You got like a base down here. I shouldn't call it a base. I should call it a stand, not to be confused with a base like the chemical. You got a stand down here with like a tower kind of thing and a clamp on it, right? This is to hold something called a burette. I spell it like that. Some people just say like B-U-R-E-T. There's different spellings. Burette, though, that's how I prefer to spell it. A burette is basically the special device that allows you to slowly add drops of whatever your titrant is into your solution that you want to see change color. So for instance, perhaps we would put an acid in our Erlenmeyer flask, plus of course our indicator, because the indicator is what's going to tell us that we've done is correct. It's going to change color. In this burette, though, you're going to fill it up with, I guess in this case, your base. It doesn't have to be a base in the burette. You can put acids in burettes and have your base down here too. It really doesn't matter. It all depends on what you're looking for. So again, don't go thinking that the base has to go in the burette. But anyway, you'll fill up the burette. It's always a good idea. Use a funnel, of course. You don't splash it all over the place. Leave a little air gap so the air can come out so it doesn't swoosh out and all that. On the burette, there's a bunch of little lines. You don't have to fill it all the way to the top because sometimes you only need to like fill it up a little bit. Basically, though, when you start, you got to take an initial reading of your burette, right? This is kind of an inverted scale. You'll notice the very top is set at 0, and then it actually increases as you go down. But basically, you take your initial reading, and then you have like this little this thing here. They actually call it a stopcock, and you like open it, and it allows just small drops to come out one at a time, right? So it really, really slowly lets some drops through. And you basically, as you're watching it really close, like your face is pretty much right up against this. And then like you let it drip, drip, drip. And as soon as it changes color, you immediately shut this, right? And then you take a final reading and then, you know, whatever, right? Also, while it's dripping, you can actually hold it with another hand and swirl this, right? So you get like an even distribution. Yeah, it's kind of cool. Anyway, the video that I've shown or that I've posted shows the actual process. It even shows the color change way better. In person, I'm hoping we can do this, of course, once things return back to normal. This is like seriously like my favorite part of Chemistry 20. I love doing titration reactions. Like it's just interesting. It's so hands-on. But anyway, just good to know. So here's some other important notes on titrations. I'm just going to fly through this real quick. There's a subtle but slight difference between titrating a strong acid with a strong base. So in other words, if you had a strong acid down in your Erlenmeyer flask and you're dropping a strong base into it, here's what the curve is going to look like. I'm going to do this really Mickey Mouse. It doesn't have to be perfect. You guys can get the idea. Here's your pH. We got 0, 7, and 14. And then this is your volume of base added. I'm going to start like summarizing that, maybe I'll just say it's your VBA, because believe me, I'm going to like draw this same chart like 3 times. If it's a strong acid with a strong base, your initial pH is going to be really low, right? So you're going to be somewhere down here, we'll say, right? What you'll notice is when you do a strong acid with a strong base, dropping some base in there, the equivalence point really shoots up very far, very fast, and then it levels off very fast as well. So once again, that is your equivalence point. Your equivalence point. There we go. Now, what if we had a weak base down in our Erlenmeyer flask? I'm going to draw an Erlenmeyer flask just for fun there. Here. So what if there's a weak base down here, right? What the heck? What is that going to look like? Here, let's see. So we'll draw another chart. Again, I'm going to be lazy. Volume of base added, it's your VBA. Here's pH over here. That's already, shortened up, so that's all good. We got 0, 7, 14. Here's what's going to happen when you do a weak acid with a strong base. A weak acid is going to have, of course, a higher pH, but still less than 7. What you're going to notice, it actually has like this greater buffering capacity. So in other words, it like holds on to it for longer. And then like it'll eventually actually just shoot up, but it won't go super far, right? Subtle difference, but that's basically all you really need to know there, okay? So buffering is just where the acid is like doing its thing. It's neutralizing the base, or in this case, the base neutralizing the acid. As soon as that buffer is used up, boom, it shoots up. You got your equivalence point, just as you would before. Another thing just to mention, it is in your notes right in the center there. I'm just like reading it real quick. There is one equivalence point for every H plus transfer. Did I include that? Maybe I put that on the next slide. No, I didn't, right? So every time in your acid, for every H that exists in there, or H positive, I should say, there's going to be one equivalence point. So certain graphs could actually have more than one equivalence point, and it won't always be based around a pH of 7 necessarily, which is why we won't really deal with those as much, but still, it is kind of cool. So just so you can get an idea what a graph of that would look like, we call it a polyprotic acid. That just literally means an acid with more than one hydrogen. So maybe I'll even write that on the side here. Polyprotic. Polyprotic is an acid with more than one H positive. So a good example, we've already dealt with it today. I think we dealt with it today. H2SO4, sulfuric acid, that's a polyprotic acid. So in other words, you'll actually have two equivalence points. If we're going to draw our chart once again, volume of base added, pH 0, 7, 14. This one will look more like this. You'll have a low pH, and then it'll like shoot up suddenly, but then it'll flatline right here, and then it'll shoot up again, right? It's not that this whole inner segment is your equivalence point. It's actually that you'll actually have two equivalence points because it's polyprotic. And matter of fact, because there was two hydrogens here, there's two equivalence points. If there was H3 something, right, you'd have three equivalence points, but this would be your equivalence point 1, and this would be your equivalence point 2. Not super important for this course. You don't need to worry about that too much. What I do want you to worry about a little bit more are ones like this, right? Especially strong acids with strong bases, because that's really what we're going to be dealing with 99% of the time. So we're going to do an example. This is the only like draw a curve example that we're really going to do here. We have a beaker that contains this much H2SO4. Oh, it says beaker. It really should have been an Erlenmeyer flask. Shame on them. A graduated tube, so a burette, is used to slowly add NaOH solutions. So in this case, we actually have our base in our burette. Cool. At the instant that 15.6 milliliters of the 3.2 mole per liter, that's what capital M means, mole per liter solution of NaOH has been added, that is, the equivalence point has been reached, right? And then the titration process is stopped. So of course they would have seen some rapid color change at that point, so they would have stopped the whole situation. So step 1, draw your titration diagram and curve. Just noting here, I see it says diagram and curve. Interesting. In my notes, or at least for now, maybe I'll fix this. I only did a curve. I'll start with a curve. So with our curve, it's the last one we'll do today, I swear. So volume of base added. Matter of fact, you know what? I'm going to go back. I'm going to rescind on that. Not volume of base added. We're going to be more exact here because we know what base we're dealing with here. We'll say this is the volume of NaOH added. And pH, of course, always goes here. It's just 0, 7, 14. We know we're dealing with H2SO4, and that's in our beaker. It really should be in an Erlenmeyer flask, but whatever. I'll be pedantic about that later. H2SO4 has a very low pH. It's a strong acid. So I'm going to start down here, and then we're going to have our equivalence point, and it'll level off. What's interesting about this graph is, though, we can actually add one more detail here that we weren't able to on those previous graphs on other slides. And that's the actual volume that brought us to our equivalence point. Notice it was 15.6 milliliters. So I might as well write that in there too, 15.6 milliliters. Bingo, bango, bongo, we got it, right? No big deal. We got our equivalence point. Awesome, that's our titration curve. Titration diagram, this is kind of silly. I feel kind of weird doing this, but I'll do it anyway. If we're going to draw a titration diagram, it literally is like, okay, draw your stand. Okay, it says a beaker. I'm going to say, you know what, forget that noise. I'm going to draw an Erlenmeyer flask because that's just who I am as a person. There we go. Holy Toledo, look at that. That is a perfect Erlenmeyer flask if I've ever seen one. Now, this is going to contain H2SO4. So maybe I'll even label that. That's our H2SO4. And then we need our burette. So of course we got to have our clamp. We got to safety first here, guys, right? We got to actually like clamp this in. And then we'll have this going on. And then like a sharp point. I'm not going to like put it right in there, even though it usually should, but I don't think I'm that skilled of an artist. And then we'll have like a little bit of base in here. So there's my fill line. I'll even point to it and just say, you know what, this is going to be my NaOH solution. Awesome. Oh, you know what I should also say? This is H2SO4 down here. I should also say plus an indicator, because it'd be useless without an indicator. You'd just be like adding drops. You wouldn't see anything. You just see a chemical reaction happening. You'd be like, oh, cool. And it would happen the whole time, but there wouldn't be a color change. You wouldn't know when you hit your equivalence point, right? So you need an indicator in there. Should also draw that little stopcock thing. It's just gonna be like a little lever thing. Like it literally just looks like a tap. It's not really a big deal. It's not the most crazy thing. And I guess that's it. That's my titration diagram. Don't really know what we're getting out of that, but cool. Hey, at least we know. Awesome. All right, step 2, 3, and 4. These are a little bit more mathy. Step 2, figure out your balanced equation. Well, we know it's H2SO4 plus NaOH. That's a classic acid plus a base, so it's going to produce HOH, that's water. And then our salt, quote unquote, which is going to be sodium sulfate, but sodium has a positive 1 charge, so we have to make it Na2SO4. And then just balance it. I'll put a 2 in front of here, a 2 in front of here, and now we're good. Step 3, list your givens and your unknowns. This is a bit of a different way of doing it, but one given that we know is we know we have 3.2 capital M, which is moles per liter, and 15.6 milliliters of that H2SO4, right? So we know how much, oh wait, was it what was it? No, it wasn't H2SO4, fake news right there. Sorry about that, guys. It's NaOH, my mistake. We know how much of that we have, right? 15.6 milliliters. That was how much was actually dripped into our quote unquote beaker. So that was how much came out of the burette. Their first reading and their final reading, they just subtract the 2, and that was how much they actually added into there. What we don't know, however, is our concentration, certainly, because we're looking, or at least we probably should find that concentration of this. That's the whole point of a titration experiment. So we don't know our concentration, an unknown moles per liter, but we do know our volume of our H2SO4. That was 0.0250 liters. See right here. Okay, that was how much was actually in that flask. Okay, and again, that was of your H2SO4. So using Stoich, calculate the molarity of your unknown solution. Well, I guess since we know our concentration and we know our volume, we can just multiply those two together. So we got 3.2 moles per liter equals some number of moles over 0.0156 liters. So that's going to tell us how many moles of I guess, NaOH that we have. So it's going to be N equals 0.04992 moles. And that is of our NaOH, which I want you to note is 2 parts. So NaOH, OH, which equals 2 parts. We're interested in our H2SO4. Notice there's only 1 part of it, so we need to divide it by 2. You're going to see that N is going to equal 0.02496 moles, and that's of your H2SO4. Last but not least, the question's saying calculate the molarity of your unknown solution. That's what we always do with titration experiments. We always try to find the concentration of our unknown solution. Concentration or molarity is just your number of moles divided by your number of liters. We know how many liters we have. It's right there. So our concentration equals 0.02496 moles over 0.0250 liters. Throw that in your calculator, and we have got, oh, it'll actually be a weird number. It's like 0.99 and then a few other decimals. But notice in this question, you only need 2 sig digs. Back to the original question itself. I'll even show you. Look at this. 2 sig digs. Yikes. So 2 sig digs, 0.998 whatever is actually going to round all the way up to 1.0 moles per liter. So we're already like almost 31 minutes into this. I apologize for such a long lesson, but we've got one last question to go. One last question. Holy smokes. This right here is showing you a table that would be the results of a titration experiment. Okay. So it says the titration of 25 milliliters of a 0.5 mole solution of KOH with an unknown concentration of phosphoric acid. Since it tells us an actual known volume of an actual known amount of solution, I feel pretty confident and say that this is not what's actually being dripped into the solution, but this is what's actually sitting in the Erlenmeyer flask. Okay. What is being dripped into the solution, by the sounds of it, is whatever the difference is between all these burette readings. Notice they spelled burette a little different this time. That's fine. But the differences between all these burette readings is what's actually being dripped in there. It looks like in this case, they're actually dripping in the phosphoric acid. Kind of interesting. Two things weird there. They're actually like, one, they're putting the acid into the burette, which all the other examples we've done is the base has been in your burette. But again, it doesn't matter. The other weird thing about this is the unknown thing seems to be in the burette this time, whereas before, unless I'm mistaken, the unknown thing was in the flask before. I guess it really doesn't matter. Basically, here's what we're going to do. Step A, complete the above charts. They filled in, they took their initial and their final burette readings, and they noted a color change. Only in trial 1 did they have a really strong color change, and you're going to see why in just a second. The color change was it turned bright yellow. All these other, because they said color change, I'm going to kind of assume that there was indeed a color change, because if there wasn't a color change, they would have said none. But it does say dark yellow for all of these, so I'm going to assume it went from something to dark yellow. We don't even know what indicator they used here. It didn't even say in this question. It's kind of a bogus kind of question, but still, let's figure out the change in volume first. Change in volume is just going to be the final minus the initial. So this first one is baby food. It's just 21.2, easy. Next one, 41.1 minus 21.2, that's going to be 19.9. Same with this next one, 19.85 minus 0.15 is 19.7. And then this last one, 39.6 minus 19.85 is 19.75. Just remember, burettes operate a little bit differently. A full burette has a lower number reading. So in other words, with a reading of 0.00, that burette is like literally full to the top, right? So that thing is like stuffed full. By the looks of it, it's like they did an experiment where they did one trial and then they still had enough left in their burette to do a second trial. And then when they were down at this low, or like the burette's almost empty here, if it was like a 50 milliliter burette, let's say, they went, oh, we got to refill it, but they didn't refill it all the way. Just amateur hour right here. I don't know what they were doing. Anyway, what I wanted you to notice is this first trial had the highest change in volume. So this is one where they added the most amount of acid into our base down in the beaker down below, or Erlenmeyer flask down below. And that's why we had such a different color change. It went bright yellow rather than dark yellow than all the rest. Since again, they still said it was a color change, I'm going to like take it like from them. Like the way I'd interpret this question is that all of these experiments were a success. There was still a color change, because if there wasn't, why would they have stopped? They would have could have just still gone. So I'm going to assume that all of these are a success. So we're going to consider all 4 of these trials valid. What we need to do next is find the average volume of titration. It's kind of weird that they put this into the table, because all these others are like, you don't need it in every single column. That's why I like blanked out this one whole section here. The average volume, of course, of titration is just the average of these 4 numbers. Hopefully you remember to take an average. You just add the numbers together and divide by how many numbers there were. So you just add these together and then divide by 4. I'll save you the trouble. It's 20.1. And you do have to round to sig digs here, because again, we're just making assumptions about how accurate we're doing our measurements. Next up, calculate the concentration of phosphoric acid using the average volume. I don't know why it's screaming that at us. I think that's why I threw this in here. Calculate the concentration of phosphoric acid using the average volume. It's just like they're screaming. It's like, oh, what was it? Like, what was it doing? Like, I'm just looking at this right now. I put this together like 2 years ago. Why this? Like, this is like that scene from Full Metal Jacket. It's like, show me your war face. Ah, that's a war face. All right. Anyway, we're going to move on. We got to do the concentration of this phosphoric acid. As always, guys, write your formula out, right? So we know we're adding phosphoric acid to, I think it was potassium, yeah, potassium hydroxide, KOH. Well, phosphoric acid is H3PO4. And if you didn't know that, you got to check your acid-base chart. That's all you need. Plus KOH. It's a neutralization reaction, so you're going to be producing HOH. Ooh, that's bad. Okay, HOH plus, I guess, K and PO4. PO4 is a -3 charge, though. K is +1, so we need 3 Ks. So K3, PO4. And then we got to balance this. I think we just need a 3 here and a 3 here. Good. Next up, we know everything we need to know about that KOH. That was what was sitting down in our Erlenmeyer flask. Again, oftentimes the thing we know goes in the burette, but I guess in this case, they're doing it a little different. So we know the moles per liter, that's 0.500 moles per liter. We know how many liters were added, or really relatively, or not added, how many we're dealing with. It was 25 milliliters. So in other words, we're dealing with N over 0.025 liters. Multiply by that on both sides. You're going to get N is equal to 0.0125 moles. Now I want you to notice that's 3 parts. I'm not even going to write it out. I think we've done it enough. Divided by 3, 1 part for your H3PO4 is just this divided by 3, which is a really messy number, 0.00416 repeating. So I'll just close it off right there, moles. Okay, we're looking for the concentration of this. Okay, this, in this case, this acid was what we were dripping through the burette. So we know how many moles are required to make this reaction work. Now we just have to figure out the concentration of our solution, which was unknown. It could have been a really strong phosphoric acid, or it could have been really weak phosphoric acid. We have no clue, but we need to use that average volume because that's going to be the average point at which we noticed a color change. Okay, that average volume from before was 20.1 milliliters. So just find the concentration by taking your number of moles, 0.00416 repeating. Good enough, moles, over your average volume that you noticed that color change. So 0.0201 liters, that's 20.1 milliliters. Throw that in your calculator, and I think we just need 3 sig digs in this question. 0.207 moles per liter. Woof, this is like the longest lesson of all time, but we are pretty much done. I mean, you guys have like one more task to do. I'm done. Look at me go. Haha. So for practice, what you've got to do for today is I want you to watch the other video from Thompson River University. I posted it on Google Classroom about titration, and then complete and submit the acid-based titration steps formative task I posted. If between now and our actual lesson I've changed the plan, just go by whatever it says in Google Classroom. But as for now, this is going to be due at the end of Wednesday. Okay. Again, if it says something different on Google Classroom, if I change my mind or something like that, go by that. This video was, recorded Monday night, so no big deal. As soon as you got that all done, page 26 is where the practice is. Remember, the answers are in the back of the book. And if you haven't completed any previous pages, make sure you get that done too. Anyway, as always, I'm available in our Zoom. Be sure to go back and watch that other video, though, about how to do a titration. It's only 3 minutes long. Anyway, I'm here for you, so best of luck.